Hello everyone, welcome to this presentation. In this video we are going to see 3 ways to check a DC-DC converter model by simulation. In previous videos we have seen how to model DC-DC converters in continuous conduction mode in video power electronics number 3 and in discontinuous conduction mode in the video power electronics number 8. Now we are going to see how to use LTSpice to check the validity of the models that we have developed. We are going to use the model that we have developed for the buck converter in discontinuous conduction mode as an example, but this methodology can be employed to any other model. So in this video we will see first an introduction, then we will see 3 different ways to check our model. Of course, the first one is using the actual converter. The second one is by using the average equivalent circuits. And finally, we will see how to do it using the small signal average circuit. As we will see, the simulation speed is different. If we use the actual converter, the simulation is slower. If we use the average equivalent circuit, then the simulation speed increases, but the highest simulation speed is by using the small signal average circuit. In the previous video, Power Electronics number 8, we studied the buck converter operating in discontinuous conduction mode. We have seen the different waveforms that we have in the converter. We have calculated some parameters and also we derived the voltage transformation ratio, as we can see here, with this expression. Then we obtain the average model by substituting the switch and the diode by the corresponding current sources with a waveform equivalent to the current that is circulating through the switch and the diode, and then by averaging these waveforms, then we can obtain the equivalent average model of the buck converter in discontinuous conduction mode. We can see here the average current through the switch, and here we have the average current through the diode. Then by introducing perturbations in these current sources and taking the different derivatives against the parameters that we are interested on, then we obtain the small signal equivalent circuit from which we can calculate the different transfer functions. For example, the control transfer function, which is the output voltage versus the duty cycle, we have seen how we can make the perturbation corresponding to the input voltage equal to 0. So this is going to be a short circuit, and we are going to have here an open circuit and another open circuit here. And then by analyzing this circuit, we can obtain the corresponding transfer function. We can do the same with the other transfer functions. We have seen how to obtain the susceptibility transfer function and also how to obtain the input impedance transfer function and the output impedance transfer function. Please refer to this video, Power Electronics number 8, for more information. And in this video, what we are going to do is to check that this expression for the control transfer function is correct by doing simulations in LTSpice. Particularly, we are going to see 3 different simulations that we can do to check this transfer function. And this methodology can be applied to the other 3 transfer functions that we have seen for this converter. We are going to use this design as an example. Here we have the buck converter. We have employed here an ideal switch and almost an ideal diode also to avoid any effect of the real components. Then we have here the comparator to generate the PWM waveform for the switch by comparing a DC level with a triangular waveform. And then in this converter, with this load, we are going to operate in discontinuous conduction mode, so we will be able to check the dynamic response of this converter by simulation. Then now we can run the simulation. We can start looking at the generation of the PWM output for the switch. Here we have the triangular waveform. The switching frequency is going to be 100 kHz. This is a period of 10 microseconds. Then we have here the value of the duty cycle level, which is 0.5. And then we can see in another pane, we can see the gate signal, which is like this one in red. So now we can check in another pane the current through the inductor. So we see how the current is discontinuous. We have this interval here in which the current is equal to 0. And then we can add one more pane to check the output voltage. So here is our output voltage with an average level that we can calculate by clicking Control and here Vout. So we can see that the output voltage is 6.55 volts. So we are operating in this continuous conduction mode clearly, because otherwise in continuous conduction mode the output voltage with a duty cycle of 0.5 should be equal to 5 volts. Now what we are going to do is to obtain the theoretical response of the control to output transfer function of our converter by using WinPython. Here we have a script for WinPython in order to do this. If you are not sure how to do this, you can take a look at this video, WinPython number 3, frequency analysis and body plots. So here what we do, as you can see, is to introduce the different parameters of our circuit. Then here we calculate the output voltage, gain. Then here we include the different coefficients that we have seen for our transfer function. We have seen this in the previous video, power electronics number 8. And then here is the final expression of the transfer function. Here we calculate the frequencies corresponding to the pole and the zero just to have these values. We plot the results, and finally here we do the plotting of the transfer function, and here we obtain the values of the magnitude and phase of this transfer function for 4 different points. So now we can run the script and see the results. So here we have some of the results. The output voltage is 6.56, similar as we have seen in the simulation. The frequency of the pole is 609 Hz and the frequency of the zero is 31.8 kHz. And here we have the values corresponding to the control to output transfer function for 4 different frequencies. We can see the plot by clicking here, plot, so we can see the magnitude and the phase of our transfer function. The DC gain is around this value, 16.4 dBs. Then we have the pole and the zero at this frequency here, as we have seen in the results. So now we can do the simulations and compare the results from the simulations with these theoretical values. As we have said in the introduction, the first possibility is to do a simulation with the actual converter, as we are showing here. So what we do here is to inject a sinusoidal waveform, a small sinusoidal waveform. Here it is a sinusoidal waveform of 50 millivolts peak superposed to the signal that is controlling the duty cycle. And then we are going to analyze the output voltage, and by processing the waveforms, the results of the simulation with all these statements, then we can represent the body diagram. We have seen this in a previous video In this video, LT-SPICE number 6, open loop frequency response of a DC-DC converter. You can take a look at this video and you will find more information about how to obtain this open loop response of a converter. So now we are going to run the simulation and see the results, but we will see that we need some time to finish the simulation. We have to do a simulation with several frequencies here, so we need to do the complete transient simulation at each frequency, and this of course takes some time. So for example, if we take a look here at the output voltage, then we can see the output voltage with the superposed perturbation at the different frequencies. So now, in order to see the results, we go to the circuits and press on the keyboard Control L. We get this log file with all the information, all the measurements done at the different frequencies. So in order to do this in a graphical way, then we right click on this file and select plot, and then say yes here to combine all the complex data. So we get this new screen, and then by selecting here add traces, we add the gain, the trace corresponding to gain, and then we obtain here the corresponding response of the control to output voltage for the buck converter in discontinuous conduction mode. So let's check, for example, the DC gain. In the WinPython, we selected this point at 102 Hz, so let's use the same one, around 102, more or less would be this one. So we get a dB gain, in dBs, which is 16.5, and the phase is minus 9.7. So let's check here, 16.4 minus 9.3, so it is very similar. We could check the other points, for example this one at 10.7. Then we go to the LT-SPICE and move to 10.7 kilohertz, and we get a magnitude of minus 7.4 dBs and minus 72.2 degrees. So we can check that it's very similar, minus 7.9 dBs and minus 68.1 degrees. We can check other points and see that both the simulation results and the theoretical results match very well. Of course, as we can see in the simulation, when we are approaching the switching frequency, we can see a lot of noise here in the response from the simulation, because the perturbation frequency of the duty cycle is very close to the switching frequency, so we cannot model our system in this way anymore. Approximately the last value that we can get with accuracy is close to half of the switching frequency, so it should be around this area here. So we can see that after that we have a lot of noise and it is very difficult to obtain reasonable response. The second possibility is to implement the average model that we have seen in LT-SPICE. So we can see here on the left the average model that we have seen in the presentation before, and then we can implement this average model in LT-SPICE, like here, in which we are substituting the switch by a behavioral current source, which depends on this expression here. This expression corresponds to the current through the switch as shown here in this expression, which is the average value of the current through the switch. And similarly with the current through the diode, we implement the current through the diode using this expression here with a current source which is controlled by this expression here, which is equivalent to this expression that we can see here on the left. And note that to implement these expressions here, we use this voltage source in order to generate the value of the duty cycle as a voltage level. So in principle, with this, we can run a simulation and see how the output voltage is changing at the output. So we can measure the output voltage and see that it corresponds to the expected value of 6.55 volts. Of course, in this circuit, we are not simulating the switching behavior. So we don't have information within the switching cycle because we are doing the averaging. This is the reason why we can see here in the output voltage that we don't have ripple at high frequency. We could also even add another probe pane and see the current through the inductor. So here we could get the average current that is circulating through the inductor, which will be this value here. So with this average model, we can simulate the behavior of our converter, but only considering the average values of the different variables. Now we can use the same technique as we have seen before in order to obtain the dynamic response of our converter. We use now the average equivalent circuit model, and we are injecting here, superposed to the duty cycle signal, the sinusoidal waveform of 50 millivolt peak. Then by processing all the information corresponding to the output voltage and also to the input perturbation, then we can obtain the response, the dynamic response of our converter. And now everything is going to be much quicker, the simulation is much quicker because we are not simulating what is happening within each switching period. We are working directly with our average model. So let's run the simulation to see this. So we can see how quick is the simulation, and this is exactly for the same number of points for the frequency of the perturbation and everything. So we can see that the simulation is really quick. Now we can see also the output voltage, and it is similar but without the effect of the ripple at high frequency. So now we can again press Ctrl L to go to the log file and then right click, plot, yes, and we could see here again the results at traces, select gain, and we can see the corresponding response of the magnitude in solid line in green and the phase in this continuous line here. So we could check again the different points and see that everything is correct. For example, the gain is 16.4 dBs minus 8.8 degrees and so on. So we can obtain and see that the result is very similar to the theoretical one and to that of the actual converter. And now we can see that we have no problems here of noise, obviously because we are not simulating the switching frequency, we are not simulating what is happening at each switching period. But we know that in reality these values close to the switching frequency and beyond half of the switching frequency are not real in an actual converter due to the switching behavior. And finally, the third possibility that we have is to implement in LT-SPICE the small signal equivalent circuit, as we have seen also in previous presentations. So here on the left we have the small signal equivalent circuit, in which we have all the different current sources representing the different perturbations of the current in the switch and the current in the diode. So here we have the different parameters that we have to implement these current sources. And here on the right we can see the implementation in LT-SPICE. So this similar implementation using behavioral current sources that are going to depend on the different parameters. We are generating the signal corresponding to the duty cycle using this voltage source here. We use the dot param statements in order to define all the different parameters of our circuit and also the different parameters of the model. So here we have all the final implementation. This circuit is intended to perform only AC simulations. This is a small signal simulations. We have now linear circuit, and then we can use the .AC analysis available in the LT-SPICE to obtain directly the transfer function. And as we are going to see, this is extremely fast in the simulation because because at the end this is a very simple circuit for LT-SPICE to solve. It is just a circuit in which we are going to have sinusoidal behavior, and this is very simple for LT-SPICE to analyze. So now we can do the simulation. Note that now what we want to obtain is the control to output transfer function. So what we are doing is to making zero the perturbation corresponding to the input voltage. This is the reason why we are selecting here AC equal to 0. This is done here by right clicking on the mouse, and then we use an amplitude AC0 here. And we are injecting our perturbation into the duty cycle. So if we do right click here, then we are going to inject 1 volt of AC amplitude. The value of the amplitude here, it could be any value, because at the end this is a linear circuit, so the amplitude is not going to affect to the simulation, but it is convenient to use 1 volt because in this way the gain that we are going to obtain is referred to 1 volt, and therefore the gain is directly in the correct value for the dBs. So as we see here, we are going to perform an AC analysis from 100 Hz to 100 kHz, and using 100, the number of points within each decade is equal to 100. So we can run the simulation and see that it is almost instantaneous to obtain the result. Note that this is an AC analysis, so we don't go to the control L log file. If we press Control N, then we can see this information. We don't have anything down here because we are not post-processing the results of this simulation. We can just, in order to obtain the control to output transfer function, we only have to measure the output voltage here at the output, and then we can see directly here our response corresponding again with a dB value of the gain. The DC gain will be 16.4, as we have seen in the theoretical analysis and the other simulations, and here we can see also the phase at this frequency, and we could check the other, and we would find that both the simulation and the theoretical analysis match very well. Okay, this is all today in this presentation. Thank you very much for watching this video. I hope it is interesting for you. Let me know if you have any comment or question, and see you in the next video. Goodbye now.